All right. Hello. Sorry, took a second to finish getting ready there. Let me get rid of this stuff. All right. So we're gonna do some double integration today. Hey, there's another starting soon up here. What do you know? All right. So like I said, we're gonna get started with some multiple integration today. Let me lock this in place. I think we're good. Hello again. That's because I forgot to mute myself in Google Chat. All right. Okay. Thanks for reminding me. All right, so let's go ahead and get started here, since I've already wasted several minutes. But hopefully you all are doing well. And hopefully you've been able to check out the sample assignment. That's kind of how I'm planning on I'm planning on breaking up the exam, exam 3, into pieces that look like that, into several pieces, like 3 or 4 pieces, I think. And I'll break it up by content, so it'll be like, here's a part on double integrals, here's a part on finding max and min, here's a part on just doing partial derivatives and the gradient. I'll chunk it up. It won't be like one topic per chunk, but maybe like limits and partial derivatives will go together, chain rule and the gradient stuff goes together, and things like that. In fact, that's probably a pretty good breakup. All right. So let's go ahead and get started here. Problem 1. Number 1. So let's just start off with something simple. Integrating, doing a double integral. Here, what are we doing first? Y then x. Okay. So it's important to remember when we're doing multiple integrals, we work from the inside out. So we should kind of view, in fact, let me even put this in a different color. We should view the double integral sort of like this. And think of it as like composing functions, right? You plug the number all the way on the inside, and then you apply the next function, and then you move out and apply the next function, and so on. So it's the same idea here. So we want to integrate this function with respect to y. So when we integrate this with respect to y, integral of x with respect to y would be x times y. Because again, think of what would, if we differentiated with respect to y, we'd want to get back to x plus y, right? Okay. So that's that. An integral of y with respect to y is 1/2 y squared. Right? And then we evaluate that from 0 to 2. And here, this dx just hangs out for now. Right, so we got to compute the stuff on the inside. So 0 to 1. Here, plug in the 2 for y, and we get 2x plus 2. Right? And then subtract, plugging in 0. That's going to give us 0 plus 0. Right, so now we're just down to the integral from 0 to 1 of 2x plus 2. And when we integrate that, we have our x squared plus 2x, 0 to 1, which I'll spare you the work on this. I'll just say that's 3. There's not much reason to keep going here. All right. Yeah, simple enough, hopefully. Just straightforward, do the thing. All right. So let's go on to the next problem. Let me know if you have any questions. Let's see. There's a few second delay here. Let me see how many we got here. Okay, about a 6-second delay, even though it's supposed to be ultra low latency. Go figure. Anyway. 0 to 1, 0 to pi, y squared cosine of xy. This has got to be dx first, right? Yeah. Right, so we want to compute this integral. And again, we're going to work from the inside out when we do this. So we're doing this x integral first. So we do that. Let's see, 0 to 1. Integrate this with respect to x. And all that's going to happen is we're going to get like a 1 over y that pops out. So this is going to be y sine of xy from 0 to pi dy. Right, that's what's going to happen here. And when we plug in pi, we're going to get y sine of pi y. When we plug in 0, we just get 0, so I won't bother with that. Right, now we need to compute this integral. Right? So hopefully you remember the trick here for doing y sine of, well, basically y sine y. Right? This is integration by parts. So remember, we always pick u to be the part that's easier to differentiate. That would be y. dv would be sine of pi y dy. So then du is just dy. And v is going to be minus 1 over pi cosine of pi y. Right? So this turns into, let's see, u times v, so minus 1 over pi y cosine of pi y. This is from 0 to 1. And then minus, well, taking this minus with it, plus 0 to 1, v du, so 1 over pi cosine of pi y. All right, so when we integrate that, let's integrate this, we get another 1 over pi. It's going to be sine of pi y from 0 to 1. All right, so plug in 1, we get minus 1 over pi cosine of pi plus 1 over pi sine of pi minus plug in 0. First part's going to be 0 because of this. Second part is 1 over pi sine of 0. So this is gone because sine of 0 is 0. This is gone because sine of pi is 0. So all we get here, cosine of pi is negative 1. So we just get, at the end of the day, 1 over pi as that answer. All right, so just a little reminder of doing integration by parts. I actually didn't think if this was going to turn out to be integration by parts or not. I just sort of picked an example here. Okay. So that's it for this one. Any questions? All right, awesome. Let's go ahead and move on to the third one here. So we want to integrate from 0 to 2, from x squared to 2x of xy dy dx. So when we're doing these integrals that have functions in the bounds, literally nothing changes. We do the exact same thing. Same process. So let's go ahead and try that out. So integrate from 0 to 2. We're integrating y first here. So this will be 1/2 xy squared from x squared to 2x dx. All right, let's go ahead and sort out what this is. Plug in the 2x here, and we're going to get 1/2 times x times 4x squared, so that's 2x cubed. And then minus, plug in x squared for y, and we get 1/2 x to the 5th dx. Right? And now we just have to integrate that. So do this integral. This turns into 1/2 of x to the 4th. This one here, see the power goes up to 6, so this is 1/12 x to the 6th. And this is from 0 to 2. Right, so now we just have to plug this in. So let's see, when we plug in 2, we're going to get 8 minus 2, 4, 8, 16/3. And then minus 0 minus 0. So this is 8/3. Right, because 8 is 24/3. So, yep. All right, any questions about any of these ones by any chance? So I just wanted to emphasize here that the double integrals are really just sort of do an integral and then do another one after it. That's computationally, that's all they come down to, which is, it's kind of nice that it's that straightforward. So let's look at problem 2 here. So problem 2 says evaluate this integral, this double integral over d of x plus 2y dA, where d is the region bounded by y equals 2x squared and, let's see, y equals 2x squared and y equals 1 plus x squared. Right? So when we're doing this stuff, we really do want to always graph the region that we're looking at here. Right? I think I tried to emphasize this in the lecture videos, if I remember correctly. You know, always sketch the region of integration for these things. Always do it. That should always be the first thing on your mind when you see one of these problems. So, right, so when we do that, let's say here we have 1, 2, 1, 2. Let's see here. 1, 2, 3, 4, 5, 6. We'll see if that's enough room. Hopefully it is. Right. So 1 plus x squared. So that starts here and goes up here. And then at 2, it's 2, 3, 4, 5. Right. Kind of a bad drawing, but this is y equals 1 plus x squared. Let's go ahead and look at the other one. Y equals 2x squared starts here. And then when x equals 1, it hits the same place as both of these. When x equals 2, it's actually all the way up at 8 already. So it looks something like that. So the region we're interested in is the one in here, between these two graphs. Right? So when we're setting up this double integral, we just have to pay attention to where the graphs are. Right, so this double integral of x plus 2y dA. So what we want to do, we have a couple things to think about here. The first one is, in what order are we going to integrate the functions? Or integrate the function? Right? Are we going to do dx or dy first? Right, so again, you want to think when you're trying to set up your bounds for an integral like this, when you're trying to pick the order of integration, you want to think, are the bounds going to be easier to set up if I move from left to right or if I move from bottom to top. So think about that for a second and let me know what you think we should do. Should we try to set up the bounds left to right first or bottom to top first? Which one would give us a simpler description? Any suggestions? So what we should be wanting to do here is moving from the bottom up to the top. Because in this way, no matter which x value I start at, I'm always going to start on the green function and end on the blue one. Now, if I tried to do this from left to right, if I start up here, I would go from green to blue, and then I'd have a jump, and then I'd go from blue to green. And then down here, I'd go from green to green, and I'd never even see the blue function. So if we did this with respect to x first, the left to right direction, if we did that first, we would actually have to break this into 3 pieces. And we don't want to break an integral into 3 pieces if we can do it in 1. And if we do y first, we can do it in 1. So we want to start with the bottom function here, which is 2x squared. And then go up to the top, which is the blue one, 1 plus x squared. Sorry. And then, so that was integrating with respect to y first. One thing you should note is, like, since there's x's in the bound here, we should never be integrating x at the same time. Basically, each time we do an integration, that variable should completely go away from the problem. Right? So that takes care of this one. And then now for the x's, we just have to say, well, what's the smallest x value we could have? What's the largest we could have? Right? In this case, the smallest is over here, which is -1, and the largest is over here, which is 1. So we integrate from -1 to 1 for x. Right? And then now it's just a matter of computing this. Right? So integrate this. Let's see, so we have integral with respect to y, so this is going to be xy plus x squared, oops, sorry, y squared, from 2x squared to 1 plus x squared dx. And then, so now we have to figure this stuff out. So plug this in, we're going to get, oh boy. Let me change this one to a square bracket so we don't have a million parentheses. So plug this in here, we get x plus x cubed plus square this. We're going to have 1 plus 2x squared plus x to the 4th. Right, so that's that first part, and then minus. This one's going to be 2x cubed when we plug it in. And here we're going to get plus 4x to the 4th dx. So let's simplify what we can here. -1 to 1 of, we get a 1 of x. This is the only square as well, so 2x squared. Then we have x cubed minus 2x cubed, so minus x cubed. And x to the 4th minus 4x to the 4th, so minus 4x to the 4th. Right now we just do our usual business here. This is x plus a half x squared plus 2/3 x cubed minus a fourth x to the fourth minus 3/5 x to the fifth. Okay, that was way more than I was bargaining for. All right, so we get whatever this is. Let's see, 1 plus a half plus 2/3 minus a fourth minus 3/5 minus, plug in -1, we get -1 plus a half minus 2/3 minus a fourth plus 3/5. So that cancels and those cancel. So this is going to be 2 plus 4/3 minus 6/5. It's 30 plus 20 minus 18 over 15. 240. 32 over 15. All right, I didn't mean for that to turn into an algebra and arithmetic stream there. I figured I'd just try and knock that out as quickly as I can. But the important part, I want to emphasize, the important part of these problems is setting up the double integrals. So, the rest of this is it just goes back to Calc 1, basically, to single variable. The most important thing you could tell me about this problem is this part. Right? This is like 80 to 90% of the credit on, well, I guess we're not doing the same typical exams anymore, but being able to set that up correctly and, give justification to that, on the normal written exams, this would be like 80 to 90% of the credit on the problem, right? Because the rest of this is just like single variable calculus stuff. And this is why there's some nice questions in the homework on WebAssign. I think I picked up a few of them that have the set up the double integral and don't compute it. Those are great questions. Because you really have to know what's going on to do those. All right. We got the siren testing back there again. All right. So any questions about that? All right. Let's go ahead and do problem 3. Right. So problem 3, we want to find the volume of a solid that lies under this paraboloid. So under this paraboloid here. And maybe I'll write under this and above D, where D is the region bounded by y equals 2x and y equals x squared. Right? So when we're finding the volume sort of between two regions or under a region, it should kind of remind you of, finding the area under a curve or the area between two functions. We just sort of integrate the z value, or the function for z. We take the top function for z and subtract the bottom function for z. And that difference is what we integrate. Right? So, sorry. Let's see here. Right. So the first thing we need to do, though, is figure out this region that we're graphing over. We got 1, 2, 3. 1, 2, 3, 4, 5. Right, so let's see if we can get this here. I'm going to do this one in blue. Y equals 2x. Start here. When x is 1, y is 2. When x is 2, y is 4. There's our value. Our function y equals 2x. And then let's do this one in green. So here, when x is 0, we're here. When x is 1 in here, we're here. When x is 2, we meet up with that function. So again, we're looking at D being the region in here. So in this case, there's not really any difference whether we tried to integrate with respect to x first or y first. In either case, we're going to end up getting one integral, because this region starts at blue and ends on green if we move left to right, and it starts on green and ends on blue if we go bottom to top. So it doesn't matter which way we look at this one, which is kind of nice. Some regions are simple like that. So since we did bottom to top first last time, let's do left to right this time. So the volume here, the volume is obtained by integrating over D this function right here. So let's set up our integral. In fact, I think in the interest of actually getting through, I really want to at least do problem 6 here. So let's just set up this integral and we'll skip computing it. Because again, setting it up is the really important part here. Right, so we need to decide on an order of integration. So we decided we're going to do left to right this time. So x first, then y. All right, so that means we need to set up some bounds for x. Where does x start? Or when we fix an x value, right? So if we fix an x value here and move up, what function does it start on? What is the value for y that it starts on? Or for x, sorry. Oh, I did this all kinds of backwards. Dang it. Sorry, what we're doing here is, if we're integrating x first, we have to fix a y value. And we say, all right, when we fix that y value, what x value does that start at? And what x value does it end at? So all that means is we just have to solve these two functions for x. Right? So here, if we solve for x, this is square root of y. Here, if we solve for x, this is 1/2 y. So this one would actually look a little bit better if we did the y integral first, because then we wouldn't have to readjust the functions, but also the functions would look nicer. But it's fine either way. So here we're starting on the blue one. We have 1/2 y down here. We have square root of y up here. For y, we just need to know, well, what y value does this start at? What y value does it end at? The lowest y value is 0 here. So we're going to start there. The highest y value is where these intersect, and this is y equals 4. We go from 0 to 4. Right? So really all we're doing here is kind of just trying to describe our region. Right? Okay. So I'm going to leave it at that. Just so, because at this point it's just doing, single variable calculus and computation. I think that's less important than knowing how to set this up. Okay. Problem 4 is the exact same thing as problem 3. I did good. That was a mistake. Sorry about that. So I guess there is no problem 4 anyway. So let's go ahead and get straight to problem 5. I don't know why I put a duplicate in there. That was a mistake. So problem 5. Let's do the same thing. Instead of evaluating the integral, let's set it up and get it to a place where we could evaluate it and then go from there. Right, then we'll move on to the next one, which we will actually compute. Okay. So here we're trying to compute or set up this integral where D is bounded by y equals x minus 1 and y squared equals 2x plus 6. Right? Okay, so here, sorry. Right. So here, again, first step, always, 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 always sketch the region of integration. Right? This is always the case with these. I can't emphasize it enough. All right, so let's sketch this. Let's see. So this is a parabola that opens to the right. So, let's see. Let's rewrite this a little bit. This is going to be x equals 1/2 y squared minus 3. I'm going to do that just so I have a good idea of what that parabola looks like. So here, this parabola is going to start a bit back here at minus 3. Well, let's see. 1, 2, 2. All right, let's see where we get from here. We plug in 2. Maybe we need to go to 3. We'll see. All right. So let's start with this green one. So this parabola starts back here at negative 3. When we plug in, let's plug in y equals 2, just so we get a nice number. That's going to be 2 minus 3. So that's negative 1. So we're kind of on this track here. All right. Maybe actually let's do negative 4 as well. Let's plug in 4 next. So if we plug in 4 to this, that's going to be 8 minus 3, which is 5. Get the same thing down here. Our parabola looks something like this. It's a little bit bad drawing, but looks something like that. The blue one, right, this is just the diagonal line that starts 1 unit down. Right. So it actually does connect up at these 2 points here. Right, so these 2 connection points, these are 5, 4, and this one here is negative 1, negative 2. Right. So this is the region we're looking at here for D. So the question is, should we integrate this with respect to x or with respect to y first? What is the better choice? So I'll give you a second to think about that. And let me know what you think is the better choice for which variable to integrate with respect to. Actually, I got a package dropped at my door. So I'm going to go grab that while you think about this. All right. So hopefully you've had a chance to think about it and which one might be a wise choice. And if you look at the way I've drawn the pink lines, it kind of is given away there. But we want to integrate in the x direction first here. Right? Because again, if we tried to do this in the y direction, we would actually have to break up the integral into two pieces right here. Because the bottom and the top are both green here, but the bottom and the top are different colors over here. So when you're drawing these regions, drawing them in color if you can will be very helpful. So here we want to do x, so x is from left to right. Right, on the left edge, x is equal to this, 1/2 y squared minus 3. Right, on the right edge, we have to solve this for x. X is y plus 1, so this goes to y plus 1. Right, and then now here, for the y integral, for these bounds, we just use the y values of these 2 points here, the very bottom and the very top, -2 to 4. Right. Interesting. It booted me from the Google meeting. I don't have any dropped frames or anything, so I hope my stream is still live. Looks like it might have temporarily dipped. Hopefully we're okay now. Interesting. I always wondered if people were just like dipping in and out of the meeting all the time, but apparently you can just be randomly booted. All right. Yeah, so that's it for this problem. Again, to compute this, we would go on and, press forward with this, but we kind of did enough of that with the first problem. Right. So again, setting up the integral here is, I think, the much more important part of this problem. All right. So let's go ahead and do problem 6. Let's look at problem 6 here. Right, I think we'll actually compute this one. So we have this integral from 0 to 1 from x to 1 sine of y squared dy dx. Right? So this problem has a very important thing to it. Looking at this problem as is, there's no way we could compute this. Right? There's no way to integrate sine of y squared. All right. So what do? Well, if we can't integrate this with respect to y, maybe we should try and integrate this with respect to x first. Right? But in order to do that, we have to know, well, what are we integrating over? What is this region of integration? Because if we're going to switch the bounds, we have to know what the region looks like, because we can't just take these two integrals and flip their order. That won't even be a valid answer, because then you'll have variables out here and numbers in here, which doesn't make any sense at all. So let's figure out what we're looking at here. Right, so when we're trying to plot this, we know x, the outside one, x goes from 0 to 1. So we're only sort of interested in stuff between here, and let's say this is 1. Between here and here. All right? So that's for the x values. The y values now, one of the functions we have is y equals 1. So that's this line. This is y equals 1. Maybe I'll add in this is x equals 0 and x equals 1. Right? And then the bottom one is y equals x, which is this line. So really, when we're trying to sketch the region, we're kind of just saying, all right, this first integral is bounds for y. So say graph y equals x, y equals 1. the next integral is for x, graph x equals 0, x equals 1. And then you're looking for a region that's sort of bounded by all these things. And in this case, it's this triangular region right here. Because the bottom is x, the top is 1, so we know we have to be in here. But now this tells us how we can change this integral to be in terms of x first. Right, so being able to switch the order of integration is just paramountly important for this kind of problem. Okay. So if we integrate with respect to x first, that means we're doing a left to right approach. The left edge of this is x equals 0, so we start at 0. The right edge is y equals x, or x equals y, so 0 to y. Y starts down here at 0, goes all the way up to 1, so now we're going from 0 to 1. So if we integrate this with respect to x, this whole thing here is just a function of y, so it's just x times this number, or times this, right, from 0 to y, dy, which at the end of the day, we're going to get 0 to 1, y sine of y squared. And look, this is an integral you could do u substitution on. So I'll skip this u substitution part of it and tell you this is just going to be -1/2 of cosine y squared. I'll assume you guys know how to do u sub at this point. And now we're going from 0 to 1. So if we compute this, we're going to get -1/2 cosine of 1. And then this is going to be plus 1/2. As we plug in 0, we get cosine of 0, which is 1. So, yeah. All right. And you'd run into a similar story with problem 7. Right? But before I go on, any question here at all? All right, great. So let's look at problem 7 real quick. And I think for this one, since we're kind of just about out of time here, let's just switch the order and I'll leave off the computation of this one. So again, here we're looking at, the integral from 0 to 1, from x squared to 1, of square root of y times sine of y, dy dx. Right? So this one's a little more deceiving than the last one, in that it sort of looks like you might be able to pull off maybe an integration by parts on it. Because like if it were y sine of y, we saw this in an earlier problem, we actually could integrate that with integration by parts. This one, however, square root of y never really goes away when you take derivatives. It just sort of gets worse. So nothing here is going to get us to anything we can actually finish off. So we do have to switch the order here as well. So again, important to graph your region of integration here. Very important. So here, x again is going from 0 to 1. Here we have x equals 0, x equals 1. I like starting with the outside integral because it's going to give us the biggest restriction, and then we just sort of chop our way down. Right? Here we have y equals 1 on top. So if this is 1 right here, there's y equals 1. The bottom is y equals x squared, which is this function. So if you compare this picture we have with what's going on in the bounds of the integral, you see we have to be in this piece again, because where y is starting at x squared and ending at 1. Right? So when we're swapping the order of integration here, oops, in the other order, dx dy. Did I fix that up there? Okay. Right, so now again, when we're doing the dx integral here, we want to look from the left to the right. So at the left edge, x is still 0. At the right edge, x is ending on this parabola. So we have to solve that for x, which is, since we're on this half of the parabola, it's square root of y. And so this up here becomes square root of y, right? And then the bounds for y, we just pick the lowest y value and the highest y value, and that's it. So 0 to 1. Right? So, after you integrate this with respect to x, I'll just say here, you're going to wind up with y sine of y dy. Right? So I'll let you think about why that's true. Do the computation to check it out. And then here, you're going to do integration by parts. Okay. So any questions on these problems here? So again, the most important part of these double integral problems, in my opinion here, is being able to properly set them up. Right? And my reasoning for that is we can always tell a computer how to actually compute it, but as I think I've said before, computers are only as smart as we tell them to be. Right? If we poorly program in a computation, it's going to give us a poor answer. So we do have to still know how to set problems up. We have to know how to code in our problems to things like Mathematica or whatever other program you might use. So I'm really going to emphasize the setting up the problem stuff here. All right. So I think that'll be it for the first session here. Thanks for stopping by. Feel free to stick around for round 2 if you want, starting in about 5 to 6 minutes. And have a nice day. All right. Go again. All right. So before we get started on the problems today, which I realize I put a duplicate problem in there. So we're not going to do problem 4. That was a duplicate. So before we get started today, let me just say, hopefully you were able to see that the sample exam segment question, I posted that so you can see how the timer works. So maybe you've done it already, maybe you haven't. It's just a short one just to kind of give you an idea of what it looks like, or what the format will look like. And the actual exam will be composed of several of those, maybe 4 or 5, probably 4. But we'll see. But again, they'll sort of chunk up the topics for the exam. Sorry. So you'll have like, a piece maybe from like the start of multivariable functions through partial derivatives, maybe something on the chain rule and the gradient, something on the double integral stuff. I have to figure out exactly how I want to chunk that up. It took me way too long to figure out just how to get WebAssign to do the thing I wanted. And unfortunately, I couldn't get it to do the 20% by default. So that's something that I'll have to go through individually for everyone and check if anyone had a 0 on a part. I'll have to change that to a 20% myself, but that's fine. There's worse things to have to do. But yeah, so hopefully you get the chance to check that out. And like I said, I'll post the actual exam segments to be available on Monday, and then you'll have through April 14th to actually do them. The important thing to know, though, is the deadline is going to be April 14th at 11 p.m. Eastern. And the important thing about that is, let's say the assignment has a 20-minute time limit on it, but if you start it 10 minutes before the deadline, well, you're only going to have 10 minutes to do it. So I'll write up those details when the exam gets posted. But just be aware of that. Don't push it to the last minute. It's not going to be a good idea. Okay. So, sorry. All right, so let's go ahead and get started on doing some of these problems here. Problem 1. Got everything good? All right, cool. All right, so problem 1 here. Part 1 is we're just computing this integral from 0 to 1, 0 to 2 of x plus y dy dx. All right, so when we're doing multiple integrals, it's basically the same thing as doing integrals in single variable calculus. You just do them one at a time. So again, here we always start from the inside out. So let's integrate this function with respect to y. So we want to basically undo a partial derivative with respect to y here. So this would be xy plus 1/2 y squared. That's going to be from 0 to 2. Right? And again, think about it here. When we're doing this integral here with respect to y, again, just you can double check your answer by, if I want to integrate with respect to y, then I should be able to differentiate with respect to y and get back to this. Right? So it's always the same, basically the same logic applies to check whether your answer is right or wrong, as did when you were doing just normal single integrals. What? Okay. That was a thing that happened. All right. So let's go ahead and plug in these values. We get 0 to 1. Plug in the 2, and we're going to have 2x plus 2. Minus plug in the 0. We get 0 plus 0 dx. That's the integral from 0 to 1 of just 2x plus 2 dx. So integrate, this is now just our usual business here. X squared plus 2x from 0 to 1. And I'll spare the work. This works out to be 3. So that's it for this one. Right. So let's go ahead and move on to the next problem, unless there's any questions. One, 0 to pi, y squared cosine, it's y, dx dy. Right. So here, let's go ahead and do this integral. So when we actually, yeah, this is fine. Integrate this with respect to x, right? This is going to turn out to be negative y sine of xy, right? From 0 to pi dy. Oh, sorry, not negative. I don't know why I put a negative there. No negative. Integral of cosine is sine, right? So this is kind of a u substitution integral, if you want to think about it that way. U would be x times y in this case, but we don't really need to go that far if you are a bit comfortable with it. All right, so now that we got that, let's go ahead and work out what the inside will be. We plug in pi for x, so we get y sine of pi y. And then plug in the 0. Sine of 0 is just 0, so actually this is all we get. So now we have to integrate that. And the way we integrate this is with integration by parts. So here we're going to take u to be y. dv is going to be sine of pi y. dy. So du is just going to be dx. And v is going to be negative 1 over pi cosine of pi y. All right? So hopefully that makes sense. So when we integrate this, we have u times v, so minus 1 over pi y cosine of pi y. This is from 0 to 1. And then we would have minus v times du. So this negative here, I'm going to pull out and make a plus here. Go from 0 to 1, v du, so just 1 over pi cosine pi y dy. Right? So instead of evaluating this part now, I'm going to integrate this and then evaluate them all together. So 1 over pi y cosine of pi y. That part over here, integrate this with respect to y. and we're going to have plus 1 over pi squared sine of pi y. And this all goes from 0 to 1. So now we just plug in all this stuff. So plug in the 1, we're going to get negative 1 over pi cosine of pi plus 1 over pi squared sine of pi minus, plug in 0, right? I'm plugging in 0 here, so this whole part is 0, plus 1 over pi squared sine of 0. Well, sine of pi is 0, so this is gone. Sine of 0 is 0, so that part's gone. Cosine of pi is negative 1. So this whole thing actually just works out to be 1 over pi. Okay. Hopefully that makes sense there. Any questions about that? All right, awesome. Yeah, so, hopefully you're kind of seeing here that actually performing the computation for these multiple integrals, it's basically no different at all to what we've been doing for, or sorry, I should say what you have been doing for single integrals, right? It's like the exact same thing, you just do it twice. No big deal. So we'll see in the later problems, we'll just sort of set up things. We won't really bother with actually computing them. Let's see. So problem 3 here. This one we will compute though, just so we can have a few examples of computation under our belt. Oops, 2x of xy dy dx. Right. So for this one here, again, just usual business. Integrate xy with respect to y. So 1/2 xy squared. We're evaluating this from x squared to 2x. So plug that stuff in. Plug in the 2x, we're going to get 2x cubed. And then plug in the x squared, we're going to get minus 1/2 x to the 5th x. So when we integrate this, again, with respect to x, we're going to get 1/4 x to the 4th minus 1/12 x to the 6th from 0 to 2. So plug in the 2, we get 4 minus, what is that going to be? 2, 4, 8, 16, 16 thirds. Minus 0 minus 0.
Shouldn't it be 1/2 x to the 4th?
Yes. Yep, thank you. Yes, that's right. So this actually should be an 8, not a 4. All right. So where are we going? Right. So now we just need to do this. So 8 is 24 over 3 minus 16 thirds is just going to be 8 thirds. And there we go. Okay. Any other questions, or hopefully no more mistakes? Yeah, so the actual computation of these things, not too difficult. Well, no more difficult than doing single integrals. Right, you might still have to do U substitution, you might still have to do integration by parts, or possibly some other tricks, if you're doing it by hand anyway. But the only, I guess, sort of additional wrinkle you might have is, you now have variables of x and y. So I guess I should say, in the same way that doing partial derivatives is harder than doing normal derivatives, which, once you can kind of get a handle on treating certain variables as constants, once you're comfortable with that, then the difference between the partial derivatives and regular derivatives and these sort of single integrals and multiple integrals, the difficulty difference is about the same. So it's something that you might just have to do a couple times to kind of wrap your head around and get used to, but then they're about the same. More important though, when we're doing multiple integration, I'm sort of less worried about all this business of computation, because we have computers that can do this stuff for us. The computation part. The part it can't do is set up the integrals for us, right? We have to tell it the bounds on an integral. You might get some fancy programs that can figure it out for you. But as far as I'm aware, Mathematica can't do it, at least. So we have to know how to set up these integrals. So for the next problems, 2 through 5, I want to just worry about setting up the integrals for these rather than actually computing them. Because that's the real valuable skill here. Once you've done that, it does kind of just turn back into Calc 1 or Math 135. So problem 2, right? So here we want to evaluate this integral, x plus 2y over d, dA, and d here is this region bounded by y equals 2x squared and y equals 1 plus x squared. Right. So all we're going to do in this problem, at least here in the stream, is just set up the integral to a point where we're ready to compute it. Right? And then actually for the lab on Friday, I'll put in there some stuff about like how do we integrate, how do we differentiate, or like do multiple integrals, how do we do partial derivatives and gradients and all that stuff. How do we do that for functions of multiple variables? Anyway, so let's go ahead and look at this. So whenever we're doing these problems, and I'm pretty sure I emphasize this heavily in the lecture videos, always, 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 and then always sketch your region of integration. Right? This is the most important thing for these problems. So here we want to sketch these two things so we can figure out what does the region look like. Because once we know what it looks like, we can set up the bounds. Right? So the graph of this thing. Is this enough? Good. 2, 1, 2. Should be good. All right, so I'm gonna go away. I'm gonna graph this one in blue and this one in green. Right. So for the blue one, right, when x is 0, y is 0. When x is 1, y is 2. When x is 2, y is 8. It's like way up there somewhere. We have some steep parabola here. Now for this one, when x is 0, y is 1. When x is 1, y is 2. Likewise, when it's negative 1. When x is 2, y is 5. Let's see. Which is this. These go up quite quickly. 5. Right, so that's the green one. I wanted to make sure it didn't look like these two crossed over here because they don't. This blue one's like way up here. All right. So looking at this, now that we've plotted these two, we can see the region that these two functions, the graph of these two functions bound. That region D is this in here. Right, this is the only region that's actually closed off by these two graphs. So the question then becomes, when I'm trying to compute this integral, when I'm trying to set up bounds for this, the question is, in which order do I want to integrate? What order do I want to set up the bounds? Do I want to do the x integral first or the y integral first? And the way to answer that is look at your shape here and decide, would it be easier to look at this function or this region kind of left to right or top to bottom? Right? Which way makes more sense? Right? I mean, we can always do either one, but we want to pick the one that sort of has the easiest description. So this region here, is it more easily described by saying what the top is and what the top is and what the bottom is, or what the left side and what the right side are? Which one is easier situation?
Would it be bottom and top?
Yeah, exactly. It'd be bottom to top here. So when we're looking at this one, if we tried to describe it from left to right, we would end up with 3 different pieces. If we did left to right, we'd have sort of this piece up here. This would be one part. This would be another part, because here the left is blue, the right is green. And this chunk here, the left is green, the right is blue. And in the bottom part down here, the left is blue and the right is blue. So if we're moving left to right, we'd have 3 different double integrals to set up for this. But if we move bottom to top, well, the bottom is always blue, the top is always green. That's all we need to know. So that means if we're going bottom to top, we're moving in the y direction for that integral. So we need to integrate y first. Oops. Integrate y first and then x. Okay. The bottom function is the blue one. So the bottom is y equals 2x squared. The top is 1 plus x. So y equals 1 plus x squared. Right? And then for x, all we're doing is, I forgot to label these. All we're doing is picking the smallest x value to the largest x value. So the smallest is over here at -1. The largest is here at 1. This just goes from -1 to 1. Right? And then at this point, it's just a straightforward compute this integral, plug in some stuff, compute the next integral. Hopefully nothing too challenging there for that part. But again, this part right here is by far the most important part of this problem, setting up this integral. Because again, as I was saying, this is something the computer won't be able to do for you. You have to tell the computer to compute this thing here. But again, at this point, now it's just computation. So we'll sort of step back from the problem here. Any questions about this one at all? I think I figured out we have about a 6-second delay here, so I'll few seconds here. So let's move on to problem 3. So problem 3, this one says we want to find the volume of the solid that's under the paraboloid, z equals x squared plus y squared, and above the region D, which is bounded by y equals 2x and y equals x squared. So we want the region, so we have a solid here that kind of sits above whatever shape D is and has, imagine sort of like this is the roof of the building. Imagine it as a building. The base, the floor of the building is the region D here, and the ceiling of the building is this function here, or the roof of the building. Right? So when we're trying to find volumes of things, right, much like when we're sort of finding area underneath a curve, or say area between two curves, we just sort of take the top minus the bottom. And here we have the top, the bottom sits in the xy plane, so it's just integrate to the function. So here the volume is just going to be this integral here. So we want to compute that, and that's going to give us the volume. Okay. So what this means now is we just have to figure out what does this region look like and how to set up bounds for it. So let's graph these, right? That's how we'll set up bounds. Let's see. Let's do it here. 1, 2, 1, 2, 2, 3, 4. All right. So again, I'll graph this in blue and this one in green. So the blue one here starts at the origin at x equals 1, y is 2, x equals 2, y is 4, x equals -1, y is -2. Here's our blue function. Y equals x squared, just the usual parabola. So again here, once we've graphed this, we want to look and see, well, is there any region that's kind of closed off by all of this? And there is, and it's this one right here. Sorry. So now that we have that, we want to ask the question, well, in what order would it make more sense to set up this integral? Is this region easier described in a left to right sort of fashion or a bottom to top fashion? Okay, so think about that for a second and let me know what you think.
That would be left to right.
Right. So left to right works here just fine. And actually bottom to top also works just fine, right? So this works great in either way, because if we did left to right, you know, we have the blue line here is always the left. The green parabola here is always the right side. So moving left to right, fantastic, no issues. Also, moving bottom to top, the bottom is always green, the top is always blue, no matter where we are. So actually, either way works out to be just fine here. So since it was suggested bottom to or left to right, let's do left to right. Sorry about that. Right. So if we do left to right, we're integrating x first. Okay. So we have to come up with, well, what is x equal to on the blue line and what is x equal to on the green part? Okay. So over here, basically what we have to do is solve these for x. Right, so here x is going to be 1/2 y. So we'll pop down here and say 1/2 y. On the right side here, we have y equals x squared. So if we solve for x, we actually have to take the positive square root of y, because over here x is positive. So square root of y. And then now that we have that, for the outer integral, we just pick the lowest value of y and the highest value of y, which in this case are 0 and 4. Right? So yeah, this integral, it doesn't matter which way we set it up to do the computation. I will say the bounds will look a little bit nicer if we had done y first. So if we did y first, the reason it would look a little bit nicer is because we wouldn't have to solve these for x, and they're already solved for y. So if we're doing y bottom to top, the bottom would be x squared, the top would be 2x, and then x goes from 0 to 2 here, which I realize is almost exactly the same as part 3 of problem 1. In fact, the bounds are exactly the same. So this is the region of integration in problem 1-3. Interesting. I didn't even think about that. All right. So any questions about this at all? And by the way, what I'm saying here with this is fine as an answer. Or sorry, as an integral to compute. This is perfectly 100% correct. But so is this one. And it doesn't really matter at all which one you want to do. They're both going to work out to give you the exact same answer. The question is, which one do you want to do? Right? And, just pick the one that works best for you. If you can see this region better as a left to right versus a bottom to top, go for that. Right? But I just want to say either setup is 100% correct here. And I just realized that this is very wrong. That should be saying that. We'll just call that an April Fool's joke. All right. All right, so any questions about this one? Awesome. All right, so 4 was an accidental duplicate of 2. So we're just going to go straight to problem 5. And again, I just want to set up the integral here. I don't want to bother actually computing it. So we're trying to compute this integral where d is bounded by y equals x minus 1 and y squared equals 2x plus 6. Right? So we need to, again, first things first, always just graph the function. Right? So I'm going to graph this one in blue and this one in green. And to make this graph a little easier, I'm going to solve this for x. So this is going to be 1/2 y squared minus 3 if I solve that for x. So this is going to be a parabola that opens to the right. So let's go ahead and graph this. One, two, that's -3 here. Go to 1, 2, 3, 4. 1, 2, 3, and 4. Let's see. 2, 3, 5. I think that's enough. Let's see. So y equals x minus 1. Pretty simple line to graph. Deal there. This parabola here, right, just kind of imagine we were graphing this as, y equals 1/2 x squared minus 3, but then turn it on its side. So it starts over here when y equals 1, or sorry, let's do when y equals 2, x is negative 1. We got one here. We get another one down here. When y is negative 2, we get the same thing. And then I'm going to jump ahead to y equals 4. That's going to be 8 minus 3, which is 5. So that's actually this point over here, this point over here. Yeah, close. Right. So we have, this is our graph. So think of the region that's bounded here, and think, is this better to use to integrate with respect to x first or y first? In other words, should we integrate from left to right first or bottom to top first? Think which one would be better in this situation.
X first?
Yep. Yeah, integrating with respect to x first here is much better. If we tried to integrate with respect to y first, we would have to split this region here, because in the y direction, in this part, the bottom and top are both green, but over here, the bottom is blue and the top is green. On the other hand, if we integrate with respect to x, no matter where we try to integrate from, or whatever, no matter what y value we start at, it's always left on the green, right on the blue. Right? So whenever you're doing these problems, I always, encourage sketch the region and then imagine drawing lines in here like this and see, well, which way does it make more sense? Which way is it easier to describe? So x first is the situation here. So starting on the left, we have the green function, which is this right here, which I conveniently already solved for x. So 1/2 y squared minus 3 on the bottom. On the top, I need to solve this for x. That's just y plus 1. So no big deal there. And then for the outside integral, I just picked the largest and smallest values of y, which are these here. So that's, this one's -2, this one's 4. And there you go. That's all there is to it. So again, this is the most interesting part of this problem, of these problems, isn't really the computation itself. It's managing to set up the bounds correctly. That's by far the most interesting part of these problems, because again, that's the part that a computer can't just compute for you. All right. Any questions on this one? Excellent. Let's look at problem 6 here. So in problem 6, we're trying to integrate from 0 to 1, from x to 1, sine of y squared, dy dx. All right. So looking at this one here, we want to ask, well, can we do this integral? And as it stands, you might remember, we can't actually integrate sine of y squared. So, well, we have to do something about that. And thankfully, unlike if we were, if we had a single integral, we'd sort of be stuck with it. Now, actually, interestingly enough, starting in, when do we start this? Week after next, I think? Where'd my schedule go? There we go. Yeah, starting week after next, we're going to talk about how we actually could try to integrate something like sine of x squared dx. But for now, we can't really do anything about it, so what we need to do here is switch the order of integration and hope that helps. In order to switch the order of integration, we have to be able to read the region of integration off of the integral here. So the way to do that, the way I like to do this anyway, is I'm going to start with my outside integral and the variable here. So I know this is x. These are bounds on x right here. So what I'm going to do is, let's say here's x equals 1. I'm going to draw the equations x equals 0, x equals 1, which are the y-axis and this horizontal line. Right, so start with the outside integral. You can start with the inside integral as well. I like starting with the outside one because it kind of cuts off the region you have to worry about. Right. And then now we're gonna do the inside integral is for y. So I'm going to graph y equals x and y equals 1. Let's say 1 is about here. Here's y equals 1. And here's y equals x. All right, so now that we've got this, there's two regions closed off here. So we have to be able to look at the bounds to know which one we actually want. And if we look at it, we know y starts at x and ends at 1. So we're interested in this spot right here. Right? So with that in mind, we can switch the order of integration. Sine of y squared dx dy. Right? So when I am now doing this with respect to x, I'm now switching from a left to right perspective first. The left edge is 0. The right edge is this line, y equals x, so that's y. And then y, the lowest value is 0, the highest value is 1. So it's 0 to 1. So what you want to be really, really careful about is if you're trying to switch the order of integration, you can't just take these two integrals here and swap their order. It's a little more subtle than that. Now, if all four of these are just numbers, right? If it's like, 0 to 1, 4 to 2, or something like that. If everything is a number, yeah, just flip them all day. It doesn't matter, right? That's sort of what Fubini's theorem tells us. But if you have variables, if you have functions in your bounds, you have to be a bit more careful. Right. So now we should be able to do this. Let's go ahead and compute this one. Right. So integrate this from 0 to y. Let's see what we get here. So all of this is just a function of y, so it's a constant as far as x is concerned. You'd get x sine y squared from 0 to y dy, which is 0 to 1. You're just going to get y sine of y squared dy. That's it. Right. Integrate that with respect to y, and you're going to end up with negative 1/2 cosine of y squared from 0 to 1. Right. And again, this is just a u substitution here. This thing on the inside would be u. I'll let you think about why that should be true. And, now just plug this stuff in. So we get minus 1/2 cosine of 1, and minus 1/2 cosine of 0. So this is 1/2 of, I guess 1 minus cosine of 1 would be the answer here. Whatever that happens to be. Any question about that one? All right. So let's go ahead and look at the last one here. Problem 7. All right, so problem 7 here, we're trying to compute the integral from 0 to 1, from x squared to 1, of square root of y sine of y, dy dx, dy dx. Oh. Right. So again, this one's a little more subtle than the last one. This is sort of a function we obviously know isn't integrable, or in terms of elementary functions, it is integrable. This thing here, this is a little more deceiving, because we can integrate something like y sine of y. But when you throw in that square root there, integration by parts isn't going to save you anymore. There's no way we can actually pull this one off. So we actually need to switch the order of integration again. So let's sketch our region here. Here I know x only goes between 0 and 1 again, so I'm going to worry about the first quadrant. Here, x equals 0, x equals 1. Was a very bad line. Let's go with that. All right, so again, the outside numbers are for x, and the inside bounds are for y. So I'm going to graph y equals 1. It's supposed to be blue. Y equals 1. And this time, y equals x squared. Right? And again, we just have to think about, well, what is the region of integration here? If we look at the bounds, the bottom for y is x squared, the top is 1. That puts us back in here. Right, so kind of similar region to the other one, but that's okay. All right, so if we're trying to switch this order of integration, then root of y, sine of y, dx dy. Right, for x, again, we're going to look from left to right. The left edge is x equals 0. What is the right edge of this shape? What x equal on the right edge here?
Square root of y.
Yep, square root of y. Square root y. And then for y, again, we're just going to look at what's the smallest value and what's the largest value. So 0 to 1. Okay. So I think since we're about at the end of the class period here, I'll do the first integral. Or I'll tell you what it is. We're going to wind up with this, which is now something we can do. Right, give me 1 second real quick. All right. So, yeah. I won't finish this one off. I'm not sure what the answer will be off the top of my head either. But, yeah, so hopefully this order switching thing makes sense here. And again, the biggest importance here is being able to tell what the region of integration is. Because when you know the region, you're able to set up the bounds pretty easily. All right. Any questions about any of the problems here? Or questions you'd like to ask? All right, then. So I think that'll be it for today. And just a reminder, so this stuff right here, this is the last stuff for the exam material. So so it's ending at this double integral stuff here. So next Monday we'll still start with polar integration, but that won't be on the exam. All right. So with that, if you have any questions. Otherwise, have a good afternoon, good rest of your day. I hope you all are doing well and your families are doing well as well. Yeah. Take care. I'll see you next time.